The last concept I want to talk about today is stress concentrations. St. Venant's principle. If you're far enough away from a point of distortion or the applied load or so on and so forth, the stress will be uniform. Well, what's the exact opposite of that? If you are very close to a point of an applied load, a drastic change in geometry, so on and so forth, then you are going to get extremely non-uniform stress distributions. So a fine example here would be kind of right by a hole. So if you have a hole in the middle of your diagram, then when you're close to it, at the cross section where the hole is, then essentially what's going to happen is you get these lines of force that kind of need to curve around the hole, and they kind of get bunched up near the edges of the hole. So what you're going to end up happening is you're going to get a higher stress kind of right by the hole and a lower stress distribution near the edges. So that'll be compared to, say, the average stress distribution evenly distributed amongst it. Same idea, say, for a fillet. The distortion essentially causes higher stress distributions kind of at the corner of the fillet, and then in the middle it's going to be less. So again, if we want equilibrium conditions to be met, if we don't want these cross sections to be shooting off into space, well then integrating the stress distribution over the entire area needs to equal to the load. That being said, we're not really too worried about the actual stress distribution. When we look at this, we're worried about what happens when it's really high. We're less worried about what happens over here. We're worried about whether or not this thing's going to fail. So we're worried about the maximum stress distribution, and then we want to be able to basically design our part so that it's able to resist the stress. So we can figure out specific values with experimental methods, advanced analysis techniques, complex simulations of the situation in question using finite element analysis or what have you. And we tend to get what we call a stress concentration factor. So this relates the maximum stress seen to the average stress. So this amount compared to what it would be if it was just averaged out. And that allows us to get these nice curves here. So again, here's a kind of an example. You can kind of see how these force lines kind of need to bunch up to curve around the hole. So we tend to get it more concentrated near the edge of the hole. So essentially, what tends to happen is that the more abrupt a change in geometry you have, the higher the stress concentration is. So if you have really small fillets in your shoulder here, then that is going to cause a higher stress concentration. If you have something like this, it's going to cause a higher stress concentration than if you had something like this. Let's pretend that those are just curves, fillets. The more gradual your geometry change is, the lower the stress concentration is. So basically, it allows more space in which your force is able to distribute itself more uniformly. Whereas the more abrupt you're going, the faster it has to happen. So it basically kind of needs to bunch up more. You can kind of see, so like for the example here with a hole on a plate, the smaller the hole is, in relation to the width, the higher stress concentration you're going to get. So essentially, we'd be kind of comparing the because this situation here, we've got a relatively large hole, so the stress has a bit more of a space to work. Whereas if we were talking a smaller hole, then essentially what would happen is that you get very little effect on the force lines out here, but very close to it you get a lot more abrupt bunching as we zoom in. So you get a larger concentrated force going on kind of in the middle there. And then so it'd be generally more abrupt. That having been said, I'm not saying that the stress levels would be higher as a result of that, because you got to keep in mind that the average stress also changes the bigger you make the hole. So that reduces the area that the hole that the stress can be carried over. So if you have a really, really wide hole, then essentially the wider you make your hole, if you increase the radius really high, then you're making this value a lot smaller, which means you're bumping up your average stress a lot higher. Whereas if you have a small hole, then your average stress is not changed very much at all. It's just the stress concentration that gets bumped up. So essentially, having a really, really wide hole doesn't increase your actual stresses. It just increases the stress concentration factor. So that's kind of one thing to keep in mind. So one thing to note, that the stress concentration factor is purely a function of geometry, doesn't matter the material. As long as the material is still a homogeneous isotropic material, as long as its Young's modulus is the same in all directions, and there's no gaps or voids or so on and so forth, then this situation still occurs. So that's how we go about figuring out what the stress figuring out what the stress state is kind of at the corner, at the very worst case scenario for your particular transition that's going on.